All right, part two. Sorry these get so long, but they're just so fun. All right, so I'm not sure how to pronounce this. I'm not an actual French person. I say Vignere. I don't know if that's correct or not. And this one has a little bit of modular arithmetic in it, kind of. It kind of reminds me of the Caesar cipher. So this one has a keyword again. We picked a keyword to kind of shift the things around in the last cipher. This one, usually you can have a short keyword and it's fine. Then we apply an alphabetical shift for each letter of plain text corresponding to the subsequent letters of the keyword. Okay, that's hard to read through. We'll just do an example. I will print this on assessments. This little chart. Notice what's going on here. It's just the alphabet that is shifted down one more letter each time. So basically, what the shift is doing, it's kind of like if D were the number 4, it tells us we're going to shift the alphabet over four letters from the original. So it's like I said, it's kind of like a Caesar, but it's a different Caesar for each word, or for each letter, sorry. So if you need to encrypt a K from a message using the letter C from the keyword, it becomes M in the encryption. Now, can you see what's going on here? Notice in column K, row C, we have an M. So when we get to C in the keyword, we're going to look through this, and then we're going to be looking in here, and then the letter we have to encrypt, it will be along the top, and the one where those intersect, kind of like coordinates, that's going to be the word for the encryption. And then if you have to decrypt that, you would, of course, look in the K row, and you look for your M, and lo and behold, it's under C. So we can kind of get backwards with that kind of inversion. It almost feels like a reflection across an axis like this, like you did for inverse functions back in transformations in Algebra 2. So it's kind of like that. Okay, so here we go. Let's do one. I'm going to use the word cobra as the keyword, and then I'm going to encrypt the letters M-U-S-T-A-N-G. So let me write that here first, M-U-S-T-A-N-G, and then what's going to happen is I'm going to encrypt those so I'm going to encrypt M using the letter C. I'm going to encrypt U using the letter O. I'm going to encrypt S, etc. Using B, using R, using A. That'll be fun. And then I start over. So whatever happens, you just keep cycling through this keyword to encrypt the next thing. Okay, so as I encrypt that, I need to encrypt this letter M using the letter C. So I'm going to look in the row for C until I find, and then under the M, I'm confused because of the example I just used before. I'm trying to encrypt M using C. So I look in the row for C, and I go until I'm under the M, and that turns into an O. Gosh, a lot of repeated letters here. Okay, so that's where I'm at there. To encrypt U using O, I'm now in the row for O, and I look until am under the U. This is kind of hard. It'd be nice if I had a ruler. So I'm in the O row, in the U column. I believe this is an I. Right here, this is under the U. And I'm looking in the B row, and I want to be under the S. That's a little easier because it's close to the top. That's a T. Whoops, I should put some spaces there. That's a T. And then in the R row, etc. And there's the rest of that word. And notice this is kind of a silly one, in the A row under A, I just found A again. So that can happen. You can get kind of the same, under the A row, I think things aren't going to change at all. But think about how that feels. It's like each one of these just gives me a different amount of shift. It's like I'm using a different Caesar cipher for each word. And this just tells me how much kind of shift to use each letter as I again cycle through the letters of the keyword. To decode, it doesn't talk about that here. To decode, it's not that hard to figure out. I just kind of go backwards. Again, I would have to know the keyword to decode. It's just like you have to have the keys if you're going to unlock the word. I would use the keyword and go backwards for this O to figure out that it was supposed to come from an M. I think I would look under the O, and I would look down until I found this. Is that right? No, I would look next to the O. Just a second. Sorry, one way to do that is to look for the O in the C row. I would know that I'm using I would know the key. So I would be looking in the C row for O, and I realize that O is under M. And then I'd be looking for I in the O row. I'd find I in the O row and realize, oh, that's under U, etc. Okay. Next one is the Jefferson Wheel, and yes, this is named after one of the early presidents of the United States. He is credited with this. I don't know if he actually came up with it or not. But this is made from a physical object, or at least you can imagine a physical object as you do this. I'm sure these exist in some museums, but there's these discs that are stacked together along this central pin, and they all can spin like wheels. They can spin individually. And each one has a different scrambling of the alphabet. You can kind of see that on here. There's nothing really uniform about the way each one of these alphabets is scrambled. They're all kind of totally different. And then the other person would know that, and then they would kind of rotate them to their desires to get the message to line up here. Okay, so how does this work in terms of encryption and decryption? Okay, so yeah, not only can they rotate independently, but you could take them apart and restack them. So there's zillions and zillions of combinations. It's like a hyper Rubik's cube of letters. Okay, so the way the problems are going to work, and the way this is going to look on quizzes and tests, is I'm going to like spell out one of these, or here 5 of these potential disks that we could use. So and they'll be numbered. And I actually found a place online where I can generate random orderings of the alphabet, so that this was easy for me to just do online. So the way this works, step 1, rearrange the disk in a non-sequential key order. So they're going to give you an order of these letters, order of these disks. They might say the order of the disks is 4, 2, 1, 3, 5. And then rotate, at least conceptually, there's a letter Y there, rotate, at least conceptually, the disks until the plain text word occupies a row. And that means like, dial in your message so that it actually makes sense like that. And then the encoded message is the letters that appear in the row below the letters from the plain text. So if this was the one they were using, the encoded message is actually this. It would be found in these letters right here. That's the encoded message. And from that, we'll be able, once we know that, and we know we know the order of the disks, we'll be able to figure out what the original message was. Okay. So again, in practice, let me read that one more time. In practice, this means that you will find the letter immediately following. So imagine these as disks. That would be one kind of row along that that you could read along the row of the, along the row of the edge of the wheel, and this would be the row below it, for example. Okay, so we're going to use these disks, and of course, the number of disks has to be the same length as the length of your message. So if I was going to stack these in the order of 4, 1, 5, 2, 3, how would I do that? So basically, the letter H would be I would dial up this 4 disks. That's the first disk in the stack, and I would set that to H. The encrypted message would be the next letter beyond that, which is this letter P. So H turns into P. Look in row 1. O in row 1 would then turn into V. Oh, cool, it was house, and there's accidentally a move here. That's interesting. 5, the U would turn into V. Oh, cool, 2 different V's. And then the 4th letter S is in row 2, or disk 2, that turns into D. And in E in row 3, that turns into N. So that's how that works. Decoding, again, not bad. This is the secret that the person has to know, the secret keyword here, the key kind of number string is those numbers, and then the person would look at row 4 P and go, oh, it's the letter right before that. So they'd look in row 4 or disk 4, letter P, the letter kind of above it is H. In row 1, the V above that is O, etc. And they would figure out how that works. So that one's pretty simple, actually. All right, the Hill Cipher. This is actually the first thing we're going to do from the other book. This is from the TCMS book, and this book was written by published by the same company that does the Core Plus, which is kind of those investigative ways to kind of teach and learn stuff, which is cool, but it's kind of different. And I have, again, just like the For All Practical Purposes book, I have that scanned in online, so you can read that. There's a term that they introduced at this point, which I thought we should probably talk about too, which is this idea of symmetric key cryptography. I think everything we've done so far has been, symmetric key. Symmetric key crypto system, the same key is used to encrypt and decrypt. So like the thing we just did, where we use this stack of disks, or we use like the Mario Kart thing where we shifted everything over. We use that same, once we figure out the system, you can use the same kind of system or key or algorithm and just kind of use it backwards, but it's really the same key to use encrypt and decrypt. There's a certain level of vulnerability for hackers with that kind of system, but that's the name of that kind of system. It's called symmetric key. We're going to do some asymmetric key systems by the end of the unit. And we'll talk about more of this in person. Okay, so the problem number 4 on page 459 walks you through this Hill Cipher, and there's a worksheet after that. So we'll do the worksheet after we do this. But here's the steps. So here's one major difference. First of all, they introduce a space. The Hill Cipher treats a space as a character. So now here's kind of the bummer about this. Now the number to letter system is completely, shifted over by 1. Z used to be 25 in the old systems, and now it's 26 because we have this annoying 0 in front of everything. So if you were used to, a certain letter being a certain number, now that's like H was 7 before, and now it's 8. So there you go. And now you have to, another thing that comes up in here, because we are going to use matrices for calculation. There's the idea of an inverse of a 2 by 2 matrix. Well, inverses of matrices in general. This one uses inverses of 2 by 2 matrices. We can actually do that on the calculator, so we're not going to spend a lot of time talking about how the inverses of matrices work, but you need to use those for this cipher. Okay, so you get a 2 by 2 matrix that is going to have an inverse. It's made up of integers, and it has an inverse that has integers. That's easier than it sounds. And then you make your plain text message into numbers. First, numbers from this, this new system with 0 as the space. Wrong way. And then put those numbers into a 2-row matrix. So it's going to look kind of like this, where the letters of the word go first letter, second letter, third letter, fourth letter, fifth letter, etc. If you have an extra letter, I think you put an X at the bottom. You put I think that's what happens. We'll see that at the end. Convert the letters to numbers, and did that before. And then we multiply this, so it'll be in numbers, right, from the number chart. Multiply the cipher matrix by the message matrix. So you'll have this 2 by 2 that has the inverse times this thing. So it's the 2 by 2 on the left, I believe, and then this matrix, and you multiply it. So you get a whole new matrix that's the same dimensions as the original, but it is going to be multiplied. So it's kind of like decimation, because then the next thing we're going to do is mod it down so it could be converted back into letters. So we mod 27 now because we have 27 elements in this set. Mod it 27 and we get something we can convert back to letters. So that's all there is to it. So here's the one that comes from the worksheet. So this is the last page of your handout, but I didn't make this. This is actually right out from that book. Okay, so here's the matrix they're going to use. It's this one that's 1, 2, 1, 3, and that works out to have an inverse. Here's how you can find out on the calculator if it has an inverse. We did matrices on the calculator recently, and you can get a 2 by 2 just by going right there, and I put this matrix in, and there it is. And if I want to find out if it has a matrix, I can actually simply raise it to the -1 power and see what it gives me, and lo and behold, it's another matrix that has all integer numbers. So there I know it's invertible. In fact, there is the inverse. So as you may have guessed, we're going to need that inverse at the end to decode our message. So they have you fill this out. Remember, this is the encoded message we're going to encode, and we turn this into this arrangement first. So of course, what goes in those places? So the message is just going MEET space TONIGHT. Looks like this. And then we convert those things into numbers. Okay, so they did some of them for us. So like the E is a 5. This was an M up here. Let me go back to red so you can see that it's an answer. So in that little space was supposed to was the letter M. M of course turns into 13. This was MEET. Can't figure that out quickly. You can surely. I'll just grab it from the other page. All right, so I can see it again. So the thing down here, of course, is a T, which is another 20. The thing that's here was an N. Oh, it's a 20. The thing that was here was an N, and an N is 14, and then, of course, this is 8. That's a 14. H is 8, and T is 20, I believe. Okay, so now we have this all in numbers. All right, so now, and you might as well do this on the calculator, I want to multiply the transformation matrix times the matrix of these new numbers. And remember, you can enter a matrix like this. If you type on the 3 by 3, you can tell it how big you want it. And how big is this thing? This thing is 2 rows and 6 columns. So I could do this, 2 and 6, and then I'll get the right shape, and then I can enter those numbers in. Okay, so I can type those in, hit enter, and then it'll give me this new thing. Now, these can't be converted, all can't be converted back into letters. Actually, very few of them. The 23 can be converted back into letters, but none of the rest of them can because they're too big. The next step, just like the decimation, is I have to mod this now down to mod it 27. But the coolest thing is the calculator will actually do this as a whole matrix all at the same time. I can mod the entire matrix 27 and it will just do the whole thing. So here's the new matrix, and now this is the thing I can turn to letters. And so that we have that saved, I'll just put that whole thing on the calculator, or from the calculator on this screen. So this is the new thing, and then I just convert this back into letters from that 0 to 26 chart. So notice I converted those into letters, and then to write that as one string for transmission, I would use that. Now to get it back, to decode, I start with the inverse times this encoded thing, And then I mod it 27 again, and guess what? I get the original message back. I'm out of time, but I'll put it in the doc.